after we do this run through, I will be taking any questions that you have for the class. So I don't expect for this to take entirely too long. And afterwards, we'll be doing a Q&A to clarify any questions people have related to this or not related, whatever you need. So like I was saying, in the last month or so, we started our after exam 1 with looking at protecting group chemistry, and not just protecting group chemistry, but functional group manipulations. But first, we'll talk about protecting group chemistry. And so the crux of protecting group chemistry is that it's extraordinarily useful for protecting our sensitive functional groups. If you have a functional group on your molecule that's electrophilic and you don't want it to be electrophilic, protecting group is a great way to solve that problem. It can mask acidic protons and it can mask nucleophiles or bases in case those things are incompatible with the reaction conditions that we're looking at. And so the first protecting groups we talked about were the carbonyl protection. And this is pretty straightforward. The go-to way we have for doing this is to take our aldehyde, which we know aldehydes are electrophiles. So if we don't want our aldehyde to be an electrophile, we can protect it using ethylene glycol and an acid catalyst. This makes a cyclic acetal, which is no longer electrophilic. And we know that acetals can be cleaved under aqueous hydrolysis conditions. So in this case, it's acid. And so in this way, we can protect our electrophilic aldehyde in case we wanted to add a Grignard or something to another part of a molecule, and then reveal it later on. We also learned alcohol protection reactions. So we know that the lone pair of alcohols is nucleophilic. And we also know that the OH of alcohols is acidic. Right, and so these can both cause a lot of problems in our chemistry, and so we need to have a robust way of protecting the alcohol group or the hydroxy group. So we learned a couple of ways to do this in class, more actually than I'm showing right now. And if you're confused on any of these, I recommend you check out your notes or ask a question. But one of the go-to ways we can do this is by using TBS chloride to make a silyl ether. So this TBS group is silyl dimethyl tert butyl.
Tert butyl. Oh, my microphone's not.
Yeah, dimethyl tert butyl silane. Yeah, and so this is a silyl ether, and they can be cleaved by fluorides. So TBAF is tetrabutyl ammonium fluoride, and so it's essentially a source of F-, right? And so fluoride nucleophiles are very good for cleaving for oxygen silicon bonds because they attack silicon. We form an intermediate like this. And then this collapses to reveal our alcohol. A good question here is, can we use any of the 3 reactions listed? All 3 of these reactions are useful. They're slightly different, but for the most part, especially these first 2, very similar in terms of their utility. And so I would say, yeah, go ahead, use a TBS protection, go ahead, use a benzyl protection. Notably, these lone pairs in a silyl ether or benzyl ether are still relatively nucleophilic, whereas in this third case, they're no longer nucleophilic or as nucleophilic. So yeah, here, the second option here is to make a benzyl ether. And so the benzyl group BN looks like this. Oh. right? So it's a carbon and then a benzene ring, and then these can be cleaved by hydrogenolysis. And so a hydrogen gas with a palladium on carbon catalyst can cleave benzyl ethers. And a third example here is the acetyl group. We can put these on with acetic anhydride and dimethylaminopyridine. There's other ways we can do this. Acyl chloride will work just fine. And this makes the acyl group. This is a little bit different than the others. It looks like this, and the electron withdrawing nature of the acetate group diminishes the nucleophilicity of the oxygen lone pair. Still slightly nucleophilic, but it's less so. And these can be cleaved under aqueous hydrolysis conditions, either acidic or basic will cleave. Okay, so that's the alcohol protecting groups that we've learned so far. We also learned amine protecting groups. A question in the chat is, why do I write a hydrogen gas and palladium and carbon in this notation? So the palladium / carbon here means it's palladium affixed to a carbon support. So these are just a heterogeneous catalyst. It's just the way people write it. And then this was supposed to be a comma. So it's hydrogen, comma, palladium on carbon. So these are the two reagents in the reaction. And so for amine protection, we learned that carbamates are a great way to protect amines because amines are very basic. So their lone pair is quite basic, and they're also nucleophilic. And so amines on their own can be very tricky to work with, and a way of lowering the reactivity is to append an electron withdrawing group to them. And so a good example of that is the Bach protection. And so that makes this carbamate shown here. And this, once again, diminishes the nucleophilicity and basicity of the amine lone pair. And Bach groups can be cleaved under acid hydrolysis conditions. Similarly to the alcohol, we can also protect these as just amides, and amides can be cleaved in a similar way as the alcohol group. Notably here, a key reaction that we learned is the DCC coupling of amines. So DCC is a reagent that allows the direct coupling of amines and carboxylic acids to make amides. I recommend that you check out your notes on how the DCC coupling works. But this is a pretty powerful reaction for making amide bonds. Okay. Any questions on protecting group chemistry before we move on? Like I said, this is just an overview. I can go into depth on anything, but this is more to point out to you what you are uncomfortable with in this chapter, so you know what to study for before tomorrow. Yeah, so what is the DMAP for? So DMAP is dimethylaminopyridine. Looks like this. It is basic at pyridine here. It's basic at pyridine, and it's useful for base catalysis. I can post these slides after the review session, and I'll post the recording too. So DMAP is useful for base catalysis, and so it is particularly useful for the generating of, for example, the acetic anhydride reacts with DMAP to make it makes this as our activated electrophile. And so this activated electrophile accelerates the reaction. And so DMAP is a great nucleophilic basic catalyst. You can use other bases. For example, typically people might use alkylamines like triethylamine, but DMAP is a really great one, and it tends to be the go-to. Someone asks, is there a time you would prefer to use FMOC over BOC? Yeah, they're cleaved orthogonally, so I didn't put the FMOC protecting group up here. You can see it in your notes, but the FMOC group can be cleaved under mildly basic conditions, whereas the BOC group is cleaved under acidic water conditions. And so these two, you see, if you wanted to remove something under basic conditions, you'd use an FMOC. If you wanted to do it under hydrolysis conditions, you'd use a BOC group, and in that way, you get orthogonality between the two. In general, what are some giveaways when working on a problem that protecting group is necessary? That's a great question. I think that if you have an unprotected amine or alcohol and on your molecule and you're using strong bases and you don't want to deprotonate those things, that's a great time to use a protecting group. If you are using Lewis acid catalysts and you note that you have these Lewis basic groups here, like the alcohol and the amine, then you want to protect them in order to not shut down your Lewis acid catalyst. So those are two times I'm normally thinking about protecting my functional groups here. When I'm thinking about protecting carbonyls, it's about making sure that they're not electrophilic. Okay, let us move on then. So after protecting group chemistry, we started to talk about the way we can interconvert functional groups. How does DMAP work on a carboxylic acid? DMAP doesn't really work very well on carboxylic acid. That's why we need a more specialized reagent for those couplings like DCC. So for carboxylic acids, we'll use DCC. DMAP is great for activating anhydrides or esters. So after we learned about protecting group chemistry, we learned about oxidation and reduction chemistry. These are the ways that we can navigate oxidation level in order to do the important chemistry that we want to do. And so we talked about a lot of different ways to do oxidations and reductions. I'm going to kind of list the ones that I think are maybe the most relevant, and the utility of these reactions is endless. If we want to prepare an electrophile, we can oxidize an alcohol to an aldehyde, and now we have an electrophile. In many cases, we just want to navigate oxidation states for the molecules that we want. So these reactions you really should know and understand, and they should come very readily. I think between protecting group chemistry and oxidation or reduction chemistry is like the very useful day-to-day chemistry where they should come very quickly to you. Like if I want to oxidize an alcohol, how do I do that? You should know right away. So these are the kind of things that you want to study. Flashcards for these work really great. So I do think that this chemistry is very important. And so for oxidizing an alcohol to an aldehyde, we learned that the Swern reaction, or we can use the reagent PCC, which is pyridinium chlorochromate. Both of these reactions work well for the oxidation of alcohol to aldehydes. And we know that we can go down in oxidation states. This is a reduction reaction through the use of reagents such as sodium borohydride. This is essentially a source of H- and allows us to navigate down oxidation levels. So you want to be familiar with ways not only to go up in oxidation level, but down in oxidation level. And I do recommend you look in your notes to look at these two reactions for sure. If we want to go up to oxidation levels, the Jones oxidation is a great way to do this. So definitely check out your notes as to how the Jones oxidation works. But this allows us to go up to oxidation levels. And if we want to go down to oxidation levels, reductions with lithium aluminum hydride is our go-to. We learned some other ways in the class where we can stop at only reducing, we can only go down one oxidation level. I haven't included that here, but feel free to check out your notes for that. Okay, so if you want to go up to oxidation levels, and for some practice, this is obviously oxidation level 1. This is oxidation level 3. Oxidation level 1. Oxidation level 2. right? So if we want to navigate oxidation levels in these ways, we have different reagents and different reaction conditions to do so. Another oxidation reaction we learned is the Baehr-Villiger oxidation. The Baehr-Villiger oxidation is a very useful one for the transformation of ketones into esters. And for unsymmetrical ketones, we learned that the bond at which the bond at which oxygen inserts into is based on the migratory aptitude of the groups. And so we'll find that when doing these, oxygen is more likely to insert into hydrogen and then aryl bonds, and then tertiary, secondary, and primary carbon-carbon bonds. So someone in chat asked, what are the oxidation levels? The second row, right reactions, and some people are saying 4 and 1. So the oxygen is definitely 1. The alcohol is definitely 1. Esters are a little trickier to count because do you count the methyl group or not? Depending on who you ask, this will be 3 or 4. It's a little ambiguous. It's purely semantic. We wouldn't ask a question like that, so I wouldn't worry about that too much. I kind of consider, I'm really thinking, when I think about esters, I think about this group, so I'm thinking about oxidation level 3, but it's ambiguous, depending on how you think about these things semantically. Someone asked, do we need acid for Baehr-Villiger reaction? The MCPBA as a reagent is nice here. Metachloroperoxybenzoic acid, in that it is both acidic and an oxidant. And so it can provide itself with an acid required to do the Baehr-Villiger reaction. So as long as you use enough MCPBA, you can do Baehr-Villiger reactions. And so the order of migratory aptitude in the Baehr-Villiger reaction is hydrogen, and then our aryl groups, this is like benzene, any kind of substituted benzene, then tertiary centers and secondary centers, then primary centers. And so in this case, when we have a phenyl group, if it's under the aryl category, and it migrates preferentially over the methyl group. Okay, so the Baehr-Villiger, the book puts tertiary carbons over aryl groups. Is this correct? Not necessarily the way I learned it, but I can check on that. Ultimately, maybe they're pretty close, so maybe we'll put an equal sign. But we wouldn't have you decide between the two on the exam. So just remember that aryl and tertiary groups are faster than secondary and primary. Okay, oh, gotta delete some. Okay, other reduction reactions that we learned are the Wolff-Kishner reaction or the Clemmensen reaction. So the Wolff-Kishner reaction works through the condensation of hydrazine onto our ketone, and then basic treatment will allow for the total reduction of a carbonyl at oxidation level 2 to oxidation level 1 alkane, or oxidation level 0 alkanes. The Clemmensen is another way of doing this. You can also form these functional groups here called thioacetals, just like a acetal, but sulfur. And so thioacetals are very useful because they can allow for the reduction of thioacetals using hydrogen gas and rainy nickel. Okay, and so someone asked in the chat, other than, yeah, and so we'll actually get to that in 1 second. We also learned that alkenes can be hydrogenated using hydrogen gas and palladium and carbon support. And so that can take us from oxidation level 1 alkenes to oxidation level 0 alkanes. And we also learned that the Lindlar catalyst system can allow us to take oxidation level 2 alkynes to oxidation level 1 alkenes. And the crucial component of this is the poisoning of our palladium catalyst using this quinoline molecule after the first reduction. And so the reaction does not have time to go to the second reduction. And so this very useful catalyst system can allow us to preferentially form cis alkenes. And so this is a very useful reduction reaction. Someone asked, so the Baeyer-Villiger reaction could be used to oxidize an aldehyde to an acid, right? And that's correct, though it's rarely ever used for that. We have some, we'll learn some other chemistry probably later in the course that's a little better suited to that task. But it could, for sure. And someone else, other than Lindlar and the Lindlar catalyst and the dye-ball reagent, did we learn about any other reducing agents that just reduce once? That's mostly what we've learned, yeah. Can you explain more when you would pick to use one of the different reduction methods? There are any reduction methods that will not reduce alkenes or halides? Can you clarify the question, actually? What do you mean?
Yeah, I was curious, like, if there would be any, like, I know, like, Wolff-Kishner and Clemenson and rainy nickel all reduce, like, carbonyls, but I was curious if sometimes molecules have an alkene or a halide that could be, like, I don't know, potentially reduced also by a reduction method. And I was curious if there was, like, a method that would be favorable or
yeah.
sensitive to that. Yeah.
Yeah, no, that's a good question. I would think that so the most selective for carbonyls is going to be the Wolff-Kishner reaction. So this is pretty specific, right? You have to condense the hydrazine beforehand to do this reduction. And so it's very targeted toward carbonyl groups. The Clemenson reaction is a bit more promiscuous. It can do some other things, and of course, in the thioacetal reduction, we have to use hydrogen gas and rainy nickel, and so that can also reduce alkenes. So this is a great point in that both there's some promiscuous reactivity here. I would say my go-to would be for answering these questions would be the Wolff-Kishner reduction. Right, it's very targeted toward carbonyl groups. Doesn't react with a ton of other stuff. So that would be my choice. If you have other electrophilic sites, it might be challenging, especially if you had like base labile things, then I would avoid using that. So because we do have to use a base like potassium hydroxide. So if you have a group that would be cleaved under hydroxide conditions, you wouldn't want to use it. But this would be the first one I would think about using. And then I would think about using Clemenson or making a thioacetal and reducing it. And so really the way you want to look at this is what are the conditions of each of these, right? So in Wolff-Kishner, it's basic conditions, right? So if you have things that are sensitive to base, you don't want to use it. Clemenson is acidic condition. So if your things are very sensitive to acid, you don't want to use that. The thioacetals under hydrogen reducing conditions. So if you have alkenes, you don't want to use that, right? And so if you think about it that way, maybe you'll get a sense of which one to use when. In real life, you just use all three and hope that one of them works. But if I was writing a problem, that's the way I'd be thinking about which one I would start with doing. Any more questions? Okay. Let us move on then to, oops, same slide again. I know. Wow, somehow I got into a strange loop. Here is also a miscellaneous reaction that we learned in class, which is the Gabriel synthesis of amines. I didn't really know where to put this because it's not an oxidation or a reduction, but it is a very useful way for us to prepare primary amines. Typically, if we wanted to make an amine, we run into a problem. For example, if I wanted to react this amine with this alkyl bromide, I would get a mixture of products that would look like this, but also this, but also this, but also this. And so this is a big problem. And so a way to solve that is this very clever use of the Gabriel amine synthesis, in that you can take a phthalimide. So this is a phthalimide. Someone at some point decided it was a good idea to put 4 consonants right in the row there. So it's a phthalimide. And it's great because this amine, the lone pair is caught up in resonance between the 2 carbonyl groups. So it's not particularly nucleophilic. And so it needs to be activated by a base. So normally we'll use sodium hydride. And so sodium hydride will deprotonate to give us this amide, which can then displace our alkyl halide of interest and get us to a product that is just mono-substituted. And then the imide group, or the phthalimide, can be cleaved using hydrazine or potassium hydroxide. So it's either aqueous hydrolysis conditions or hydrazine is just a good nucleophile. It'll attack the carbonyls and displace our amine to give us the primary amine that we wanted all along. And so the Gabriel amine synthesis is a nice workaround for getting to primary amines of interest. Will we have to be able to synthesize that reagent, or can we just use it? Yeah, you can just use phthalimide. This is widely available, super duper commercial available. So you can just buy it. Any more questions on this slide? Okay, moving on. And so once we learned about oxidations and reductions, we turn to the next big meaty part of the class, and that's electrophilic aromatic substitution. So if oxidation and reduction reactions are reactions that you should know in a flashcard way, then electrophilic aromatic substitution reactions are ones that you want to understand very deeply. as they're our go-to way for making carbon-carbon bonds and functionalizing molecules in this class. In electrophilic aromatic substitution, the general scheme looks like this. We have an aromatic group that attacks an activated electrophile. This breaks aromaticity to form what is called a Wieland intermediate. The Wieland intermediate exists as a series of resonance structures wherein positive charge resides ortho and para to the arriving electrophile. And then elimination of a proton from the Wieland intermediate restores aromaticity. This is the major driving force of the reaction, in that we gain a lot of energy back from restoring aromaticity. Breaking aromaticity in the first place is quite challenging to do, and that's why it requires activated electrophile species. We'll note that reactions in electrophilic aromatic substitution are accelerated by electron donating groups, ortho and para, to the incoming electrophile due to the fact that they can they can donate electron density to the formed positive charge in the Wieland intermediate. And so in this way, we stabilize positive charge, and so electron donating groups help with electrophilic aromatic substitution. And so we learned a bunch of reactions for electrophilic aromatic substitution. I have just started listing out some here. I probably missed some, and this isn't meant as necessarily a comprehensive list, but to try and get at some of the key pictures that we see in electrophilic aromatic substitution chemistry. And so the first reaction maybe that we learned was the halogenation reaction. And it uses a halogen source of some sort, normally chlorine and bromine, and the Lewis acids like iron tribromide or iron trichloride. And what is important here is that the active electrophilic species is some sort of X+ species. So this is the bromine ion, cation, or the chlorine cation. And those are the activated electrophile. And so you can look at your notes to see how the Lewis acid here facilitates the formation of X+, but one of the keys here is that X+ is our activated electrophile species. And all this electrophilic aromatic substitution chemistry, we're looking at gaining an activated electrophile. So you want to protonate something, you want to form some sort of cationic intermediate that is the electrophile by which the benzene will attack. And another reaction that we learned is the nitration reaction. And so in the nitration reaction, the mixture of nitric acid, sometimes with itself or sometimes with a partner acid like sulfuric acid, can lead to a dehydration process and the formation of the nitronium ion, which is a highly electrophilic nitrogen source. And so this is the activated electrophile that comes in nitration chemistry. This is another case where we form an activated electrophile and attack it with the benzene ring. And then we have our Friedel-Crafts reaction. This is a classic reaction for the formation of carbon-carbon bonds. And so one way we can do that is the Friedel-Crafts alkylation, which we take an alkyl chloride, treat it with aluminum trichloride. This means our activated electrophile species is R+. Now, there's some challenges associated with this. There's some challenges associated with this in that the benzene ring can very readily alkylate more than once. And so that's a challenge. Another challenge is, depending on the nature of our R group, is carbocationic rearrangements. And so if we were to form this as our activated electrophile, it can undergo a 1,2 hydride shift to form a different activated electrophile. And depending on what we want, this can be a problem. And so the Friedel-Crafts alkylation is a very useful reaction, but when we are looking, when we crave more selectivity, or to be very careful about only alkylating one time, we can turn to the Friedel-Crafts acylation reaction, which installs an acyl group. And so important to the Friedel-Crafts acylation is the formation of the activated acylium ion. And so with the acylium ion, it does not undergo carbocation rearrangements, and the product that you form is less active than the starting material, so it's unlikely to undergo further reaction. And beyond that, the Lewis basic functional group of the ketone can coordinate away our Lewis acid, and that further shuts down overreactivity. Okay, so there's a couple of questions here. For the nitration, do we have to indicate fuming sulfuric acid? You do not. I just remember a question about oxidation whenever you have time. Does the Jones oxidation also cleave protecting groups that are cleaved using mild/strong acidic conditions, Bach and THP? Yeah, so that can be a problem with the Jones oxidation, is that it's not very functional group tolerant. There are some solutions out there for these reactions, some more mild ways to do that oxidation. The Jones oxidation is kind of the classic. But as you correctly pointed out, the Jones oxidation takes place under acidic aqueous conditions, which is not very functional group tolerant. Another question: if you use one equivalent of RCl of your alkyl chloride, would the alkylation happen once, or would there be a mixture of products? So this is referring to the Friedel-Crafts alkylation reaction. And so you would get a mixture of products most of the time. You would probably, the major might be the monoalkylation product, but the challenge there is that as you add R groups to the ring, it becomes more active, right? And so it's more nucleophilic toward your alkylation reagent. And so it wants to keep adding. You can play around with this with like reagent control or like addition times, things like that. So you could potentially see monoalkylation as the major product, but you do often see a mixture of products in those cases. Yeah. And that's just a tricky based on the activation process that's happening here. Yeah. And then one last reaction, or not last maybe, but one more reaction that I'm going to talk about today is the sulfonylation reaction. And so this uses fuming sulfuric acid, which is a very useful reaction for us because it's reversible. And so you can put on a sulfonyl group using fuming sulfuric acid, and then you can remove it using dilute sulfuric acid in water. And so this is a very useful group for us to be able to install, maybe block a position, and then we can also remove it. So that is a very useful reaction. Any questions on electrophilic aromatic substitution chemistry part 1? Okay, then we're going to move on to electrophilic aromatic substitution part 2. In this regard, this is a way for us to think about what happens when we're trying to do electrophilic aromatic substitution when we already have a substituent on the benzene ring. Okay, so this is a very important time to remind you all of the nomenclature of naming groups on benzene rings, and they're all named relative to each other. So if we say this R group is our reference point, the position adjacent to it on the benzene ring is the ortho position. One further is the meta position, and the one across from it on the benzene ring is the para position. Now, of course, these are all relative to each other. So these two hydrogens are ortho to each other. These two hydrogens are meta to each other. It's all about relative positioning. But what we've learned in class is that depending on the nature of the R group, it can direct substitution toward ortho, meta, or para positions. And so what we've learned is electron donating groups direct ortho para, and electron withdrawing groups direct meta. If you have both an electron donating group and an electron withdrawing group, the electron donating group wins out. And so what are some examples of electron donating groups? Alkyl groups are electron donating by virtue of induction. So they have a lot of carbon-hydrogen bonds that are not very electronegative, so they push electron density into the ring. Strong electron donating groups are those that have lone pairs that can delocalize charge into the ring. And so if you see a substituent with a lone pair on it, then you will say to yourself that this is, for the most part, electron donating. The exception, this is an electron donating group that directs orthopara. The slight exception to this rule is halides, which still have these lone pairs. And so since they can donate electron density into the ring using their lone pair, they are still orthopara directors. However, they're like slightly electron withdrawing. And this is because they're electronegative atoms, and so they can draw electron density away. So for example, you have the aniline here is an electron donating group that pushes electron density into the ring. Electron donating group, orthopara director. Chlorines, a little different, slightly deactivating, but still orthopara directors. And then you have a classic example of an electron withdrawing group, like the nitro group. This is a strong electron withdrawing group, and it's a meta director. And so the way you can think about this is that the electron withdrawing group can accept electrons from the ring. Therefore, it is electron withdrawing, and it is a meta director. Electron donating groups can donate electron density into the ring. So if you have a lone pair that can donate, you want to think it's an electron donating group. If it has a pi system that can accept electrons, it's electron withdrawing. Yeah. Someone asked, can you explain why ketones and esters act as meta directors? That's for the same reason as the nitro group. You can imagine them accepting electron density from the ring in a resonance structure that looks like this. Right, and so in that way, it's drawing electron density out of the ring. Yeah, and so I see a couple of questions here. Can I explain what it means if an electron donating group directs? Yes, I can. So for example, if I had a situation like this, where I had an amide, which is an electron donating group because it has a lone pair, and I also have a nitro group, which we know is an electron withdrawing group, right? So if the nitro group we know directs meta. So the nitro group wants to direct here. The amide directs ortho-para, right? So its preferred positions of substitution are here, here, and here. So in the case when we have both, if one is an electron donating group, it's the one we listen to, right? So in this case, we'll see substitution at this position, and this position. We will not see it at the position dictated to by the nitro, right? And so in this way, when you have two groups of conflicting directing group positions, you listen to the one that is more activating, that gives more electron density to the ring. Okay. Our aryl groups, biphenyl ortho-para directors, in general, yeah, they are ortho-para directors. We didn't talk about any of those examples because they're a little trickier, but they are in general ortho-para directors. If an electron withdrawing group is ortho to an electron donating group, would there be? Okay, so let's draw that out so I can see what you mean. Oops. So if there is E, W, G, E, E, G. EDG is electron donating group, EWG is electron withdrawing group. If an electron withdrawing group is ortho to an electron donating group, would there be a preference for substitution at the position para to the electron donating group? So would you prefer to donate here as opposed to here? Well, I would say likely you would get some preference for the para position because it's less hindered. But you would see that actually both the ortho and para position to the electron donating group are meta to the electron withdrawing group. So they're electronically very similar. So I would say here is your best bet. Yeah. Do we ever get substitution between the two groups when it is hindered and when it is not? Sometimes, but it tends to be very forced. Like it tends to require very forcing conditions. So the question was, if you have two groups here and here, would you ever see substitution at this position? For the most part, the substitution at these positions are going to be favored due to the fact that this position is more sterically encumbered. But if you keep forcing it, it will eventually go. So it'll prefer to go to these positions, but if those positions are also substituted, then you can start to go to the positions in between. Okay, lots of good questions here. Any other questions, or may I erase? Okay, I'm going to start erasing. Yeah, if the para position is more, so if someone asked if steric hindrance can also direct ortho, yeah, I mean, if you're in a situation where the para position is more hindered than the ortho position, you could see ortho substitution. That's certainly possible. It's very context dependent, though. Okay. Now, what did I want to talk about on this slide? Yeah, and so now that we've talked a lot about the different directing capabilities of electron donating groups and electron withdrawing groups, we recognize that a very valuable part of this chemistry is the ability to switch between the two. Right? If we have a group that is electron withdrawing that can switch to being electron donating and vice versa, we have a lot of power. And so classic ways to do this are if you take a nitro group and you can reduce it with hydrogen on palladium, hydrogen gas and palladium on charcoal, you can get to the aniline. So this is electron withdrawing, and this is electron donating. And this is obviously, and this is a reduction reaction. And so the reverse is an oxidation reaction. And so we can use an oxidant like trifluoroperoxetic acid to oxidize anilines back up to nitro groups. And in this way, we can toggle the reactivity between electron donating groups and electron withdrawing groups. This allows for us to change what positions are being directed to on the benzene ring. Another question is, can electron donating groups also direct meta if ortho pair positions are already substituted? The answer is yes. Your benzene ring is getting very full at that point, but you can direct to those. I guess it's not directed at that point. It's just that those are the positions available. And so another key reaction pairing here is the benzylic oxidation reaction. And so one way to do benzylic oxidations in the way we learned in class is using potassium permanganate and sodium hydroxide. And so this can oxidize benzylic hydrogen bonds. So these are hydrogen bonds directly adjacent to aryl groups. So these are benzylic. It can oxidize the benzylic position to a carbonyl. If this methyl group is not here, it'll go to the acid. This reaction can be a hard stop, but it's the one we've learned from class, and so this is a good way of oxidizing the benzylic position. And then we also know that we can reverse this reaction using the Clemmensen reduction or the Wolff-Kishner reduction, or making a thioacetal and reducing it. And so this is another way for us to toggle the reactivity. And so I think both of these are very useful for problem solving. Is there a different between potassium permanganate with base versus with acid? I've seen both. For the purposes of this class, there's not a difference. A classic reaction for this chemistry is the Sand-Meyer reaction. So the Sand-Meyer reaction is a super useful tool. Someone asked me to list everything. The Sand-Meyer reaction is a super useful tool for the transformation of anilines into other groups on the other groups of interest that we could use. And so it involves taking anilines and treating them with sodium nitrite, and then an acid is normally required to form these diazonium salts. And diazonium salts can be diversified in a ton of different ways. If you've been coming to the review sessions, you know that I like this slide a lot because it really outlines all the different ways that we can transform our diazonium salt. And so we can use copper chloride to put in a chlorine, bromide to put in a bromine, cyanide to put in a cyano group. This is really cool because we can switch from making a carbon-nitrogen bond to a carbon-carbon bond, something that's supremely useful in organic chemistry. Potassium iodide to put in iodine, hydrogen tetrafluoroborate, fluoride, copper oxide to put in oxygen, and we can also reduce off the diazonium salt using a hydrophosphorus acid. And so I do really recommend that you all keep the Sand-Meyer reaction in mind as a way of transforming anilines into a wide variety of other substrates. And we know that we can get anilines from nitro groups. And so you can switch from nitro to aniline and then get rid of whatever the carbon-nitrogen bond is to whatever you want, pretty much. A hugely versatile reaction. Another classic reaction that is a bit more esoteric, not super useful, but important to know exists, is the ipso substitution reaction. This is normally for terp-butyl groups or for silyl groups, and they can substitute off on the same position. So in this case, if you treat this silyl benzene ring with bromine, you will get bromine at the ipso position. So ipso refers to the same. So ortho is next to, ipso is the same. How do you get the silyl group there in the first place? That's a great question. Classically, pretty challenging to do. yeah, you would learn about it in some of the upper level organic classes. That's one of the reasons we don't talk about this reaction so much. But there are some ways to do it, and some ways from our very own John Hartwig. Can we replace TMS with any other group? The TMS can, the silo group can be replaced with a bunch of groups, mostly electrophiles. So like bromine, chlorine. I guess you could probably put a nitro group there or something. Maybe for your Kraft's alkylation would occur ipso. And will it always add ipso rather than sine? Yeah, so for especially for the silo groups, they're very selective for ipso substitution. So adding a group at the same position that it came from. And yeah, for anyone that is confused about what makes something an electron donating group or electron withdrawing group, there's a great table in the book. Someone pointed out in the chat, table 23-2, I believe, and it is a very useful resource for determining the strength of electron donation or electron withdrawal and who's who. Okay. Do you have any more questions? Oh yeah. Also, will it, can you replace TMS? Yeah, so I think you could use chloride, probably not difluoride. I think if you add most electrophiles, so for example, if you did a Friel-Crafts reaction, it would add ipso. But tends to be more of a surprise reaction than a useful one. Okay, so we're going to move on past electrophilic aromatic substitution part 2 into nucleophilic aromatic substitution. If in electrophilic aromatic substitution, the benzene ring acts as the nucleophile, in nucleophilic aromatic substitution, the benzene ring acts as the electrophile, just switches it around. And so if you have a leaving group on the benzene ring, it is normally required to be chloride or fluoride. In some cases, you can force with other halides and strong nucleophiles. But for really productive reactivity, you want to use fluorine or chlorine. The nucleophile adds to the aromatic ring. This forms our resonance stable anion, the opposite of electrophilic aromatic substitution. This is the Meisenheimer complex. And the negative charge can then eject our leaving group, restoring aromaticity and putting a nucleophile in its place. And so it turns out that benzene's not a very good electrophile. And so if you just have an unsubstituted benzene ring, trying to displace it with a nucleophile is quite slow. And so in this case, where we just have fluorobenzene, its reaction with the nucleophile sodium methoxide is slow. However, as we look at the Meisenheimer complex, we see that negative charge is built up in the positions ortho and para to the nucleophile in X group. And so with a buildup of negative charge ortho and para, putting electron withdrawing groups ortho and para to our leaving group can greatly accelerate the reaction by lowering the energy of the Meisenheimer complex. And so if we put electron withdrawing groups suddenly para or ortho or both to our leaving group, then this reaction with the nucleophile is suddenly very fast, and it is quite useful chemistry. And so this is an area where if you see leaving groups on the ring and you have electron withdrawing groups, you think to yourself, SNAR reactions. Another way that SNAR reactions can occur is through benzyne formation. Now, this normally requires very forcing conditions. Instead of an addition, then elimination mechanism. This is elimination addition mechanism. So in this case, we'll use the base sodium amide, which is a very strong base, and we'll use ammonia as a solvent, it can deprotonate the aromatic ring to eject our leaving group. And here our leaving group can be a little bit different than bromide or chloride, than fluoride or chloride. It can be a bromide or iodide because this reaction is already under forcing conditions and it has a different rate limiting step. This forms benzene. Now, nucleophile can attack benzene. To generate an intermediate that looks like this. Move some of the double bonds around, but it doesn't matter. And that grabs a proton from, typically from, in these conditions, from ammonia, and gives us our product. Yeah, and so the benzene reaction is another way we can do nucleophilic aromatic substitution. Now, in this case, what we have is a symmetric benzene, so that nitrogen could add to either this position or this position. And so you'll actually get 50-50 mixtures of this product and the other addition product. So I'm seeing a couple of questions. I'll take a second to answer. So someone is asking, for synthesis, if we don't need the nitro group for an SNAR reaction, can the slow reaction be okay, or do we need to add the nitro group to speed it up? Typically, this reaction is too slow to be useful. And so you really need some sort of electron withdrawing group to accelerate the process. So I would say for your synthesis problems, when planning these, you want to plan to have an electron withdrawing group or throw a para. And then another follow-up question was, how can we cleave the nitro group afterward? And I will refer you to the Sandmeyer reaction. So you can reduce the nitro group to an aniline, then form the diazonium salt, and then reduce it using hydrophosphorus acid. Okay. And then when we use methods of synthesis such as benzene, such as Grignard. Okay, so a couple of questions here. One that I'll answer in a little bit. Someone says, according to Google, potassium permanganate, this it reduces, but it actually oxidizes benzene derivatives to carboxylic acids and not to ketones. Yeah, in real life, this reaction is pretty harsh, and it tends to over-oxidize up all the way up to the carboxylic acid. But for the purposes of this class, we'll say that you can do the benzylic oxidation to a ketone. This is one of those areas where it's like you could potentially stop it, but it's a difficult thing to do. Yeah, operationally, but on paper it looks fine. Someone says which leaving groups are suitable for benzene formation. Pretty much all the halides, as well as some pseudo halides that we'll talk about in just a second. And so let me erase. So there's actually a third way to make benzene, but I've just put two here. One is the formation of a Grignard reagent and ejection of a nucleophile of a leaving group. And so if we have a disubstituted arene like this with a bromide and a fluoride, or maybe an iodide and a fluoride, we can use a magnesium reagent to make the Grignard. And so this makes the corresponding Grignard reagent, which can collapse and eject the fluoride to give us benzene. right? And so that's one way to do this. Another great way to do this is to, if we have sialotriflates, we can add a fluoride to them, and it'll collapse and kick out the triflyl group. Triflate is a good leaving group. It's kind of like a halide in that respect. And so this is another way we can form benzene. There's also a way you can form it through decarboxylation, but these are some good methods. So Fisher said in class that fluorine and chlorine work as leaving groups for SNAR. But the problem set had a benzene. So the problem on the problem set wasn't entirely clear, and we're not grading on that problem, so I wouldn't worry about it. But that substrate is suitable for nucleophilic aromatic substitution if going through a benzene mechanism, right? You could treat that compound with a strong base like sodium amide, go through a benzene mechanism, and do the nucleophilic aromatic substitution. And that's further stabilized by the electron withdrawing group on the ring. And so to another question, and that actually answers both these questions. Someone asked, when would I want to make a benzene? And someone else asked, if we're making it by these other methods, can we add other nucleophiles? And yes, you can. And so, for example, just from the problem set, we had a problem where you could add a phenyl as our nucleophile, and that could attack the benzene, or the benzene, sorry. And so you could get to a product that looks like this. And so benzene can be useful for creating an electrophilic site for a nucleophile to attack. Someone else asked why we use phenol instead of sodium phenoxide. You could also use sodium phenoxide. It's just for I guess it would be, even under TBAF conditions, it would be phenoxide. But more to the point, you can use a nucleophile like a phenol-derived nucleophile to attack benzene, or you can use a wide variety of nucleophiles here. Benzenes are quite useful for doing reactions, more reactions that we'll learn later in class. But for now, just be aware that they can be used. Any more questions? Does the base have to be sodium amide? No, but these are kind of the very classical conditions for doing this kind of nucleophilic aromatic substitution. There are other bases that you could use, but sodium amide should be the first one that comes to mind. Okay, and we'll move on to the very last thing we learned about in class, which was about heterocycles. And so in class, we kind of divided the heterocycles that we learned into two classes, which are electron-rich heterocycles and electron-poor heterocycles. So electron-rich heterocycles are good at doing electrophilic aromatic substitution. They're good at acting as nucleophiles. And so the very basic ones that we learned are pyrrole, furan, thiophene, and my personal favorite, indole, are some classic examples of electron-rich heterocycles. They do electrophilic aromatic substitution quite readily, And for pyrroles, furan, and thiophene, we number them in this fashion: 1, 2, 3, 4, 5. So pyrroles, furans, and thiophenes, when doing electrophilic aromatic substitution, favor reaction at the 2 position. Okay, so at the 2 or 5 position. So for furan, thiophene, and pyrrole, they react in electrophilic aromatic substitution, preferentially at the 2 position. For indole, the classic argument is that it reacts preferentially at the 1, 2, 3, 4, 5, 6, 7 position. So it reacts classically at the 3 position. That's a little different than pyrroles and furans and thiophenes, and we can talk about why if you'd like, but it's in your notes. But you should know that indoles react at the 3 position, pyrroles react at the 2 position. Now, the electron poor heterocycles are not very good at electrophilic aromatic substitution. These are pyridine, quinoline, and isoquinoline. They're not so good at electrophilic aromatic substitution. But if you were to force pyridine to do an electrophilic aromatic substitution, it favors substitution in the 1, 2. Right. Yeah, it favors electrophilic aromatic substitution at the 3 position, whereas quinoline and isoquinoline favor it at the at the 5 position. These are, especially pyridine is particularly bad at electrophilic aromatic substitution. It requires very forcing conditions. But if it happens, it's essentially like the nitrogen group is a meta director. Similarly, though, these are good at nucleophilic aromatic substitution. So if you had, for example, a chloride at the 6 or 2 position, it will add quite rapidly in nucleophilic aromatic substitution. Someone asked, so the electron poor heterocycles can still do SEAR? What kind of forcing conditions do we need? Yeah, they can. So it would require, like, it could do, like, for example, nitration or halogenation at very high temperatures, but it would be very hard pressed to do something like a Friedel-Crafts alkylation. It doesn't have the ability to do that. Yes, someone is asking, can I explain why aromaticity is broken when there's substitution at C6 for quinoline? Yes, I can. We can do that in 1 second. Yeah, and just a note that SNAR reactions on the electron-rich heterocycles are very slow. They're unlikely to occur. You can get away with them on indole if you had substituents on this benzene ring, but it's still quite slow. And so a question was asked why we see C5 substitution in quinoline. This is a good question. And so let's compare electrophilic attack at, sorry, actually, let's move the double bonds around for the sake of argument. Okay, so if we wanted to attack an electrophile at C5 or C6, we get to two different structures. So this is for C5 substitution here. Now, the predominant resonance structures in these systems are going to be those that do not break the aromaticity of the other aromatic ring, right? There's two aromatic rings in this case. And so the most favored resonance structures, the ones that contribute the most, are going to be those that don't break aromaticity at the other. And so in this case, the dominant resonance structure for C5 substitution is going to be these two resonance structures. Because in both of these resonance structures, the quinoline ring stays fully aromatic and intact. Now at C6 substitution, we have a positive charge here. And so the only resonance structures available to it are those that break aromaticity of the quinoline ring. And so in this way, C5 substitution is favored in that it has these two major resonance contributors that don't harm the aromaticity of the other system. And so C5 substitution is favored over C6. Now I saw another question as to why not C8. Well, in C8 substitution, the terminus here in C8 is closer to the electronegative nitrogen atom. And so there is an electron withdrawing effect from having this electronegative group nearby. And so it's just less nucleophilic than C5. And then someone asked, why is it more important to keep aromaticity of the ring with nitrogen for quinoline? It's not necessarily more important, but in order to do the substitution, we're going to break aromaticity. And it's going to be of the more nucleophilic ring, right? And so in that case, it's the more electron-rich one, which is the benzene half of quinoline. And so if we assume we have to break that half, the best resonance structures, or the most contributing resonance structures, are going to be those that don't touch the aromaticity of the other ring. Yeah, someone is saying, I'm assuming it's worse to have a resonance structure with nitrogen having a positive charge than carbon. Correct. Nitrogen is more electronegative than carbon, and so carbon is more electropositive than nitrogen, and so prefers having positive charge more. So the ring with nitrogen is less nucleophilic because the nitrogen is electron withdrawing, yes. And if you want to key yourself in, pyridine is electron poor heterocycle, benzene, pretty electron neutral. And so when thinking about that, benzene more nucleophilic than pyridine. And so we learned about heterocycle chemistry and the various reactions that they do. And one very special reaction that we learned is the Vilsmeier-Heck formylation reaction. And so that normally uses the reagent dimethylformamide and phosphorus reagent to introduce an aldehyde after aqueous workup. And so this is a powerful reaction that can actually be used on non-heterocyclic rings. They just have to be electron rich. but it's an electrophilic aromatic substitution reaction wherein the active electrophile species looks like this. And this is the so-called Bielsmeyer reagent and is the active electrophile that you form in order to formulate this aromatic ring. And so that's a brief look at heterocycle chemistry. Heterocycles are super important compounds. We have a whole class here dedicated to in Berkeley. One of the up-level classes is just about the chemistry of heterocycles. But what we learned so far is a brief look at electron-rich and electron-poor heterocycles and the reactivity. Any questions on this? Okay, so that's all I brought. And now I have my scratch paper slide for people to ask me any general questions you have with regards to the exam. I'm here to answer any and all questions for the next half an hour or so. Yeah, so Tyler asked a pretty complex question that we can talk about later. Yeah, I'm afraid that answering that question will be confusing to everybody. So we can talk about that some other time. But Audrey asked if I can go over question 2A on the practice test, which I can. Can we discuss decarboxylation and the mechanism? And do we need to know the Suzuki reaction? Yeah, so we don't need to know the Suzuki reaction, and give me one moment to pick up those things that people asked. Okay. Okay, so practice exams. So someone asked for the Bieshler-Naparowski reaction, do we need to know a reagent that does the oxidation step? You don't for now. Typically, this can be done with molecular oxygen, but some other oxidants can help. People use something like manganese dioxide, but we don't need to know it for now. Okay, can I go? So let's handle the questions on the practice test. Can I go over question 2A on the practice test? I can. So that reaction looks like this. And we want to get to a pyridone like this. Okay, so one thing we discussed just previously is that electron-poor heterocycles are good reagents for nucleophilic aromatic substitution. And so this question, when we see this chloropyridine, we should think to ourselves, this is ready for electrophilic aromatic substitution, or for nucleophilic aromatic substitution. And so we also look at this product here, this pyridone. What I will, and I think is the key to recognizing the answer to this problem, is that we recognize that this is a tautomer of, for example, this. So remember, for example, that amides can tautomerize just like ketones or aldehydes in structures that look like this. And so the key recognition here in this problem was that this tautomer, this hydroxypyridine, will actually sit as the pyridone. And so if you just add a nucleophile to this, like potassium hydroxide, it can eject our chloride to get us to this 2-hydroxypyridine, which will tautomerize to the pyridone. And so it's just a tricky SNAR question. Yeah. So someone asked, can we discuss decarboxylation and its mechanism? Sure. So decarboxylation is particularly rapid for beta keto acids. Oops. And so if you have substrates that look like this, where you have a carboxylic acid, beta to a ketone, and then we can do a very accelerated decarboxylation process. And that mechanism looks like this. It's a 6-membered transition state. Where we lose CO2 and form enol, which tautomerizes the ketone. And so that's how decarboxylation works. It's accelerated, so decarboxylation can happen spontaneously, but it's stabilized and accelerated by the presence of electron withdrawing groups beta to the acid. So this would also be fast if this group was, for example, a nitro group or any kind of group that can stabilize negative charge. Can I go over to see? Okay, so someone said 1C on the practice exam. Wait, I don't see a question 1. Let me. Yeah, so I assume you mean 2C. Yeah, okay, great. So let's do 2C on the practice exam. So 2C looks like this. And we're asked to get to here and here, as well as here. Did you have a problem with both of these? Oh, the test without answers, it starts as an NH2. Got it. Oh, interesting. And to different products. Okay, so let's do the one with from the test without answers. That's funny. Oh yeah, those are very different. Okay. Oops. Okay. So we have an aniline, and we're going to a phenyl group here, and group here. Okay, so for the one on the right, I think that this would require the Suzuki reaction, which is something we haven't learned in class yet. So I don't think that you would be expected to do a problem like this. So when we're actually, maybe for both of these, I would use the Suzuki reaction. And so I wouldn't really, these would be rather challenging to do with the chemistry we have so far. So I wouldn't worry about doing them. Yeah, so someone said, can we go over 4A on PSET 4? We can. There are a lot of questions. I'm sorry. I will try and get through them all. So 4A on PSET 4. Yes. Let me figure out how to. This is kind of a hard one to show. Catherine, is there any specific ones on problem 4A that you had a trouble with that I can just put up on the screen? It's a little hard to go through all of them. Okay, so the ones whose answers were neither. Let's just take a couple of examples. So this is the problem from PSET 4, wherein we asked you if the reagents would be good at nucleophilic aromatic substitution or electrophilic aromatic substitution. And so a few of them were neither. And so let's look at a few of these. Okay, so this one right here, this difluorobenzene, will not be very good at electrophilic aromatic substitution because it's an electron deficient heterocycle. Right? We have two fluorines, which are electronegative atoms. This is going to be, these are two electron withdrawing groups essentially. So the ring is not very nucleophilic. And so therefore it's not very good at nucleophilic aromatic or electrophilic aromatic substitution. Furthermore, their relationship to each other is meta. So neither of them is stabilizing the nucleophilic aromatic substitution of the other. And so it's not a very good substrate for nucleophilic aromatic substitution. For this example, it's a fully substituted benzene ring, and none of them are leaving groups, so it's good at neither. In this example, bromide is not a good leaving group for nucleophilic aromatic substitution, and it's situated meta from our electron withdrawing group. So it's not a good substrate. This substrate here. It has 3 electron withdrawing groups, so it's not electron rich at all, and so it won't want to do nucleophilic aromatic substitution or electrophilic aromatic substitution, and it has no leaving group, so it doesn't want to do either. And so that's kind of the story with these is they have to have you have to have either an electron neutral electron rich aromatic ring in order to do electrophilic aromatic substitution, and you need to have a leaving group of some sort in order to do nucleophilic aromatic substitution. Okay. Why does an aromatic ring with a chloride not work with real crafts to add a benzene? Yeah, so that's a pretty important question. So someone asked why can't I do this reaction? This reaction does not work. So why can't I do that? The major reason is that it does not form a suitable electrophile. So the benzene cation is extremely high in energy. Carbocation, this carbocation is not delocalized across the ring. It's stuck on one carbon, and it is on an sp2 hybridized carbon, which is more electron withdrawing, and so this is a very high energy species. And so reaction of this chloride with aluminum trichloride does not get you to a suitable activated electrophile. And so you cannot use benzene rings in Friel-Crafts chemistry. Someone asked when in like a mechanism problem, when hydrogen is taken, so in a electrophilic aromatic substitution reaction, if you had something like this, and we want to lose this proton, can we just say B? I'm fine with that. I don't mind. Okay. If I missed a question, feel free to re-up it. Don't spam the chat or anything, but there's a lot, so I'm trying my best. Okay, so back to the practice test for problem 3A. Is this another one where it was different or no? Is it the same? Yeah, so this is a typo. The product of this reaction should be and so the reaction is Audrey, do you still need me to go over how it works, or are you comfortable getting to this product now that you know that the answer in the key is a typo? Okay, so let's break it down. So the first step here is going to be a condensation of the amine onto the aldehyde. So we get to a product like this. No. We get to a product like now this is attacked by the aromatic ring, This is our activated electrophile. It's attacked by our electron-rich aromatic ring. Oops. And now we have a carbocation here and hydrogen here. And so elimination of that hydrogen gets us to the product. And so no, there won't be another double bond. Okay, so we'll keep on the theme of this practice exam very quickly. So question from 7. 7A, yeah. So ultimately, the answer to this question is something we didn't, oops. No. One moment, I'm panicking. Can you still see my screen now? Okay. So the question is with the practice exam, there is a benzyne question that gives one product selectively in a way that we didn't really talk about. So this goes through formation of benzyne and then substitution to give this product. And the question is, why is this selective for the formation of not the ipso, but the sine product? And the answer is something that we didn't talk about in class. So I would say don't worry about it. The major reason here being that the benzyne you form is not symmetric electronically, and it actually prefers to add meta to the electron donating group. But you're not responsible for knowing that. We didn't talk about it in class. Problem set 1b. Why wouldn't the nitric acid and turn protonate the aniline to make, yeah. So this is a good question. And it's generally something under our operational control. So when doing nitrations, if we use nitric acid and sulfuric acid, the aniline is protonated. Is now a meta director and substitutes the nitration meta. However, if we exclude sulfuric acid, at least for the purposes of this class, it will still direct orthopara. And now a very reasonable question to ask at this time is, well, wait a second, nitric acid is still more acidic than aniline is, is still more acidic than the ammonium salt is. So why is that? And well, while in nitric acid, the protonation equilibrium lies very heavily on the side of nitric acid. there's still a small amount of this species present. And what that'll do, this reacts very fast in the nitration reaction. This reacts very slow in the nitration reaction. And so the available amount of this unprotonated aniline will react much faster and give you the orthopara substituted problem product. And so that's the reason. But if you include sulfuric acid, the equilibrium lies so far on the side to the right that you only see meta substitution. Did we go over there? Someone asked me to go over syntheses from the previous review session. We'll do this very quickly. Okay, so let's clear the board. Okay, so someone asked if there's a faster way to do this. If you have a suggestion, I'd like to hear it, but I don't think there's a very quick way to do this. So when I look at this problem, I see I have a triply mismatched relationship here. All three of these groups are meta to each other. And that's not the relationship that any of them want to have. And so what I imagine would have taken place is that you would have had to have an electron donating group here that we're going to get rid of later. And so I'll do a nitration reaction. Then a hydrogenation reaction. And then a protection. I'm trying to write too quickly. This is acetic anhydride and DMAP. And so in the first step, I introduce a nitro group. In the second step, I reduce that nitro group to the amine. And in the third step, I protect it. Right, so this is my product after 3 steps. Now I have my electron donating group in place, right? And now I can do these substitution reactions that I've been wanting to do. And so I can do first a Friedel-Crafts alkylation. So and then a bromination reaction twice. Okay, and so that puts in all those groups. And then what we have to do is hydrolyze the amide. So we can do that with just base or acid, doesn't matter. And then we have to make the then we have to do the Sam-Meyer reaction to blow it off. So this reaction, this is a lot of steps, but I think is maybe one of the better ways to do it.
Hey, Ian,
yeah.
what if we acylate first with an acyl chloride and then nitrate?
And acyl
and
chloride.
then reduce everything with like rainy nickel.
So you're saying
Right, so we add the formal group.
Yeah, so you're saying So
Right, and then that would be meta directing.
yeah, so you would meta direct one here, right? But now you've run into a problem.
No, not the bromine, the nitro group.
You meta direct in a nitro group.
Yeah.
Okay. And then what?
And then nitrate the second time.
Oh, and then you're saying do a double Sandmeyer?
Yeah, but first do rainy nickel to reduce everything altogether. So the thiol acetal and then rainy nickel.
Yeah, okay, I see what you're saying. So you're
And then we
saying,
can do a Sandmeyer.
yeah, so I think that would also be good.
Okay, cool. Thank you.
Isolate nitrate twice, reduce twice, yeah, so that's and we'll follow through on this just for everyone to be clear. So we'll form the thioacetal out of this with then reduce with, oops. So one problem, and this is something I'm actually not sure about. I don't know if you can reduce nitro groups using rainy nickel. It is certainly possible that you can. I'm just not aware. But possible that it might work. That gets us to this aniline, and then we can use the Sandmeyer reaction to do that. Yeah, someone else asked, wouldn't the Clemmensen reduction work here too? Yeah, Clemmensen I think would be a better choice actually. So the Clemmensen reduction will reduce nitro groups. I do love Wikipedia. So someone asked a good question. Would you get all those nitrations to work since the ring is very deactivated? Yeah, it might be challenging, but let's pretend we can cook it to 1 billion degrees. Someone asked, how does the hydrolyzing step with the base work to get rid of the amide? The hydroxide acts as a nucleophile to attack the to attack the amide, and then you kick out the amide as a leaving group, or the amine as leaving group. It's not a great leaving group, but you can push these conditions with hydroxide and heat. So someone else says the last review session recorded as well. It is. There's a new folder on B courses that you can see it. I uploaded it this afternoon. Why does Friedel-Crafts alkylation only happen once? Once again, that's one of those things. You might get mixtures, but you could presumably control it operationally. So it's not a great reaction, but it's something that you could probably control, especially since the ortho positions here are hindered by the presence of the amide group next to them. And so when you have a directing group, it's a little bit easier because the second substitutions are hindered. Can I post answers to my review sheet from yesterday? I can post the slides maybe. I don't have answers in a sheet, but you can always, since the video is posted, you can skim the video and watch them. Along similar lines, when doing nitrations, can you use 1 or 2 equivalents to do a single versus double nitration? It tends not to be under stoichiometry control, but just simple electronic control. So, for example, if we do 1 nitration on methyl, we get para substitution as the major product. Now this ring is less activated than the starting material, right? Because we've added an electron withdrawing group. And because it's less activated, it's less likely to react. And so if you wanted to get a second substitution, you'd have to crank up the temperature. So if we added more heat, then we could get a second substitution. And if you add even more heat, you could get a third substitution. That's how they make this compound is trinitrotoluene or TNT. And that's how they make TNT. They just boil it in, they just boil toluene in nitric acid and sulfuric acid. Yep. I can answer questions for a few more minutes, but as you guys all log off, good luck on your midterm tomorrow. I think you're all going to do really good. So just, use tonight's lecture to point out what you don't know, and hopefully tomorrow we can all have a good time. Number one tip for tomorrow is just take your time. It's open notes, so take your time, use your notes, think it through, don't freak out, just take your time and it'll be okay. Yeah, I mean, we can't stop you from using anything, so you can use anything. You're welcome. I think I think it's gonna go pretty well. Yep, thank you for coming, everyone. Why wouldn't the reaction conditions also below TNT? That's a fun question. I think, I don't super know the answer to this, but I think TNT is one of those compounds that's actually only explosive in its solid form and not in its liquid form. So while it's solubilized under the reaction conditions, it's not explosive. But once you crystallize it, it is, or make it into a powder, it is. So that's just kind of a fun quirk of chemistry. Not positive, but that's the way most, like many explosives work. And it would explain the TNT thing. Yeah, so you were talking about, let me scroll up and see that question. Yeah, so let me just look at that problem. Well, thank you for copying it. One, two, 4, 6. So from the so I see 2 a.m. problem so far. Why does it restore aromaticity? afterward. Six, 8, 10. So this is a 10 electron aromatic system. So the whole system is overall aromatic, is it not? 1, 2, 3, 4, 5, 6, 7. It is 12, sorry. I'm tired. It is 12 electrons. Why did we end up? Yeah, not my area of expertise is these types of polyaromatic systems. But yeah, I would imagine then that it's a distorted system, so as to not be anti-aromatic. It's a good question. Yeah, and sorry if for you, I didn't realize I wasn't drawing it for those of you playing at home. So this is an anti-aromatic system, but it's also like weirdly cross-conjugated. But it forms a Wieland intermediate that looks like this. And the question is, this system here is pretty stabilized. You would presume that this extra alkene is actually destabilizing. So why is elimination favored over something like chloride attack? And my guess is probably pretty similar to Caroline's on this, is that this alkene is not really participating in the aromatic system as a whole, because it would be anti-aromatic, and so there's not a huge gain toward the chloride attack versus elimination, and so because the alkene is distorted so as to not be anti-aromatic. That's an interesting question, though. I'm not super familiar with the reactivity of polyaromatic compounds. It's not my field, but that's certainly a rationale. Yep, sorry that I don't have a more complete answer there. Okay, if there's no more questions, then how do we know when a ring goes through benzyne intermediate or Mesenheimer intermediate? Or in the presence of nucleophile. Yeah, so that's not always an easy thing to know. So the question is, I have and I react it. How do I know with a nucleophile? How do I know that I am going through a displacement mechanism, addition elimination, or elimination addition? So how do I know if it forms benzyne or not? So under most mild conditions, you're not going to be forming benzyne. It requires rather forcing conditions. So this is going to require really strong bases. So that, I think, is already an indication. So if they're not super strongly basic, then it's probably not benzyne. But there is some indirect evidence of benzyne formation. For example, if you saw mixtures. So if you saw this product plus some of this product, you'd say, oh, a benzyne mechanism is likely operable. So that can be an indirect evidence of benzyne. But really, I think a good way to go is to think it's not going to be benzyne unless the conditions are very forcing, or unless you're setting up to specifically form benzyne. And so unless given evidence to believe otherwise, believe it's a nucleophilic aromatic substitution chemistry problem. The only time, you know, if you see something like sodium amide and ammonia, that should scream to you benzyne, because those are very forcing conditions. But if you see something like sodium methoxide, you say, that's not super basic. I don't think that will form benzyne. I hope that answers your question. So on question 4 with, yeah. So that question is, yes. So so the question 4 on the PSAT has a situation like this. And it asks which positions would likely undergo SNAR. And so you can box this into this. So for the, the answer key has this position highlighted as potentially going under SNAR. We know that bromides aren't very good substrates for SNAR with respect to fluoride and chloride. Those are much better. Bromide is not very good, and so it requires very forcing conditions. And many times those will go through benzyne conditions anyway. And so this could be possible under very harsh conditions like these in order to form benzyne and do a nucleophilic aromatic substitution on this. But I think that one's pretty ambiguous, and we won't grade on it. So I wouldn't worry about it too much. Yeah, so Felix did not say whether or not you could collaborate tomorrow. Please don't collaborate. We obviously, once again, can't stop you, but it should be your own work. And, you know, you have your notes and you have the internet, and, you know, but yeah, you know. Okay, well, if there's no more questions, I have a good night, everybody, and good luck tomorrow. I think you're going to all do just okay. It'll be good. It'll be good. Have a good night, everyone.